So as we begin this practice, let's try one here where we have a force applied of 329 newtons and force of friction 175, and we want to find the acceleration of this 1700 kilogram car. So go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. All right, so the critical thing here is setting up your sum of the forces. Positive force applied plus the negative force of friction. We have 329 as our force applied. Force of friction is 175, which we'll subtract from our force applied. And then when we get our forces together, divide by mass, our acceleration will be 0.091 meters per second squared. Let's try this one here. We have a mass of 1,800 kilograms. The acceleration of the car is 1.2 meters per second squared. We want to find the force applied and the force of friction. So again, set up your forces here, sum the forces, and see if you can figure out what the force applied would need to be to have an acceleration of 1.2 meters per second squared. All right, so we set up our sum of the forces, positive force applied plus the negative force of friction, and we add the value to the other side. We'll take 2,335 newtons for the force applied. All right, so for this one, it's a 2,300 kilogram car. Let's say the force applied is 410 newtons, and let's say it's accelerating at 0.15 meters per second squared. And we want to know how much force of friction there is. So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so we set up our forces. Positive force applied plus negative force of friction equals ma. And we should get 65 newtons backwards will be the force of friction. All right, so let's go ahead and set up an incline, and you can draw this with me here. We'll have our mass here, and we want to draw out the forces. So let's again say it's frictionless. So we have our force of gravity straight down. We have our normal force, and that's it. So if you think about it, what's going to cause this to go down is the force of gravity. Now, what we need to set up is our coordinate axis. Our coordinate axis will be like this. And our force of gravity needs to be broken up, right? So we have force of gravity in the y, force of gravity in the x. And yeah, and if we know what the angle of the ramp is here, theta, we'll also know what this angle is here, theta. And you know, we can find out what force of gravity in x is, force of gravity in the y is, and you know, we'll know what's going on here. So what we're going to do for this one here, let's say that the mass is 10 kilograms, and let's say that the angle of the ramp here, theta, is 35 degrees. And we want to find out, yeah, what is the force of gravity in the x? What's the force of gravity in the y? Now, the hypotenuse here is the force of gravity, which is mg, which is mass, which is 10 times 9.8. So that's 98 newtons is the hypotenuse, right? Now, we want to find out what the force of gravity in x is, force of gravity in the y. So you're going to need your trig here. So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so for your force of gravity in the x here, that's the opposite side. So sine is opposite over hypotenuse. So we have the sine of 35 equals opposite over the hypotenuse, which is 98. So the opposite side comes out to be 56.2 newtons. And then FGY is the adjacent side. This is the adjacent side of the triangle. So cosine is adjacent over the hypotenuse. Cosine of 35 equals the adjacent side over 98 newtons. And so the adjacent side will be 80.28 newtons. And it turns out FGY here is equal to what the normal force is. They're balanced with each other. And then for the x, force of gravity in the x, it's 56.2 newtons. So if we wanted to find out what the acceleration is, we could set up the sum of the forces in the x equals ma. We know 56.2 newtons. The mass is 10 kilograms, so we could find the acceleration. So the acceleration would be 5.62 meters per second squared. So if you want to practice another one, this one here is would be an incline of 34 degrees. The mass is 10 kilograms. You can find the acceleration in the normal force. So if you want to practice that, you can. You know, if not, and you feel comfortable already with that first one, you can just continue. So go ahead and pause the clip if you want to try it, or you can let it go here. All right, so here's the solution. We should get 5.48 meters per second squared for the acceleration, and the force of gravity in the y will be 81.25 newtons. All right, so what is the weight of a 2 kilogram mass? So go ahead and pause the clip and do this, and when you're ready to check, you can hit play to continue. All right, force of gravity is mg, which is weight. Weight is the force of gravity, and we get 19.6 newtons. All right, what is the mass of a 543 Newton person? So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so mg, and we get a 55.41 kilograms, this person. All right, so we know that work is multiplying force times the displacement times cosine theta, and then theta is the angle between force and displacement. So with this first one here, a man lifts a 50 kilogram box 2 meters into the air. So let's draw that. Force applied is up, force of gravity is down, and he's lifting it into the air. So the force applied is up, the displacement is up, so it's going to be cosine of 0 degrees. As he lifts it. So it'll be a perfect amount of work. The trick here is figuring out how you're going to get the force. Now let's assume that he's lifting at a constant velocity as he lifts it. So yeah, go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so we've got our forces. The force applied is up, force of gravity mg is down, and 490 newtons is the force applied going up, equal to the weight, and the displacement is 2 meters up, and so we get a work of 980 newton meters. All right, so on this one, a man holds the box at arm's length for 2 hours as he stands still. How much work does he do? Well, if there's no displacement, we can have as much force as we want, but there is no work, right? All right, how about this one? A man holds a 50 kilograms box at arm's length for 2 hours and walks 1 kilometer forward. So here's our box, force applied, force of gravity. Okay, and then he walks forward. So this one is where, this is the classic example where, you know, you have to think about what this equation is doing. Force times displacement times cosine theta. If the displacement's to the right and the force applied is up, the angle would be 90 degrees. So even though there's force and there's displacement, there's no work. There's no mechanical work here. And so this is a classic example of that. All right, so let's try this one here. A father pulls a wagon up at an angle of 60 degrees. And we want to know how much work that he does. Now, what's nice here, if this, you know, this angle 60 degrees here, what's nice here is in the equation, it already does the trick for you. You know the angle, 60 degrees. You know how far, 10 meters. And you know the force, 16 newtons. And the reason this works is because cosine is the adjacent side. It's giving you what the force is in the x. Because there's no work done by the force in the y. There's only one done in the x. So 16 newtons times cosine of 60 gives you that force there. And we should get 80 newton meters for that. All right, remember kinetic energy is 1/2 mv squared. And we get the energy in joules. joules. So this one's a good one to practice. What's the kinetic energy of an 11 kilogram bowling ball rolling at 4 meters per second? And then what would the speed of a 0.624 kilogram basketball need to be to have the same kinetic energy as the bowling ball? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so 88 joules is the kinetic energy of the bowling ball. So therefore, we need to figure out how fast, and so it'd be going 16.8 meters per second to get the same kinetic energy, much less mass here. Now, potential energy is mgh. It's the stored energy, and we get that from a zero reference. So let's try this one here. Let's say we have a mass that's 992 kilograms, height of 42 meters, and we want to get the potential energy. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we should get 408,307.2 joules would be the energy. Lots of energy here because we have a very large mass, and 42 meters is decently high here. All right, so the conservation of energy relationship is very critical here, right? You know, the initial kinetic plus the initial potential should equal the kinetic final plus the potential final, as long as there's no friction, air resistance, or anything like that taking away its energy. So we're going to try this one here with a roller coaster car that is starting at the top of a hill and then going down. The initial speed is 3 meters per second. It's a 60-meter tall hill, so 60 meters here, and V initial is 3 meters per second. What we want to find out is the final speed. Now, when we set up this equation on your equation sheet, it gives you to you like this: kinetic energy initial, potential energy initial, kinetic final, plus potential final. So you just need to look on your equation sheet to identify the variables. We have 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. Now, we don't know the mass, but every single one of these terms has mass. So we can divide both sides by mass and yeah, and solve for what v final is. So go ahead and pause the clip and you can finish this, and when you're ready to check, you can hit play to continue. All right, so we should get 34.42 meters per second at the bottom.